she has traveled nearly 4 billion kilometers, delivered a probe to the surface of a toxic moon, and produced science 9 years longer than originally planned. She discovered flowing liquids where none were expected, phantasmagorical structures on a planet's icy rings, a weirdly breathing magnetosphere, and a possible abode of life on a tiny world with a startling atmosphere. Now, after 20 years in space, controllers have sent the Cassini spacecraft into a daring spiral to end her remarkable journey. Streaking along Saturn's upper atmosphere at more than 124,000 kilometers per hour, Cassini streams data and images back to Earth until heat and turbulence tear her apart.
Three, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn.
On the evening of October 15th, 1997,
We have cleared the tower.
a powerful Titan 4B booster leaves Launch Complex 40 at the Kennedy Space Center.
All systems go.
The product of 2 decades of intense collaboration between NASA and the European Space Agency, in particular, the Italian Space Agency.
And the solid rocket boosters have been set.
Some on Earth have protested this moment. They fear that if the launch fails, Cassini's nuclear electric generator will spread radioactive plutonium. As she glides outward on a nearly 7-year transit to Saturn, scientists organize their investigations based on past probes' findings. Their questions nest within one another, like the giant planet's concentric rings. Does Saturn have a solid surface? Or do its clouds thicken down to extreme densities, perhaps creating exotic forms of matter, like metallic hydrogen? Is there a rocky core? Why are the rings so bright? How old are they? What's going on beneath the thick orange clouds of Titan, Saturn's largest moon? How are Saturn's moons and rings related? What will this giant planet tell us about the evolution of solar systems and of life? At its distance of nearly 1.5 billion kilometers from the Sun, Saturn's orbit lasts 29.5 Earth years. Over the past Saturn year, Earth has added some 2.5 billion people. Average life expectancy rose from age 64 to almost 72. The internet has exploded. It now has almost 4 billion users, with half the world's population now online. In the time of Cassini, our world has been consumed with new ways of communicating, connecting, working, living, and seeing each other. Saturn is the Roman name for Kronos, the Greek god of time, who ate his children in a fit of jealousy. In myth, as in the ever-changing universe, time is the devourer of all things. To catch up with Saturn, mission planners have sent Cassini on a series of flybys, each time hitching a ride on the planet's gravity to speed her on her way. Pioneer 11 flew by Saturn in 1979, Voyager 1 in 1980, and Voyager 2 in 1981. Cassini will become the first craft to orbit Saturn, captured by Saturn's gravity on June 30th, 2004. Cassini's prime mission was to be 4 years, but she will remain healthy far longer. Her assignments will be extended twice, an additional 2-year equinox mission and a 7-year solstice mission. Yet Cassini's entire exploration will span less than half a Saturn year, from late winter through early summer. The Saturn system lies 9.5 astronomical units from the Sun. That's nearly 10 times farther out than Earth. The whole grand clockworks speeds along at 34,821 kilometers every hour, more than 10 times faster than a bullet fired from a gun. The planet spins fast, rotating about its axis once every 10 hours and 39 minutes. So while a year on Saturn lasts only 11,000 Earth days, it's about 24,500 Saturn days. Made up mostly of hydrogen and helium, Saturn is the least dense of all the planets. It's often said, if you could find a bathtub big enough, Saturn would float. That's not quite accurate, but its density is lower than that of the liquid water in Earth's oceans. And it's big. You could pour 764 Earths into the volume of Saturn. This mission is officially named Cassini-Huygens, honoring 2 remarkable men of 17th century science. The French-Italian Giovanni Domenico Cassini, also known as Jean-Dominique Cassini, and the Dutch Christian Huygens. Key players in the scientific revolution, they collaborated and competed throughout their lives. In the process, transforming astrology into astrophysics. As director of the Paris Observatory, Cassini built and refined long-tube refractor telescopes. But Huygens found a way to remove the cumbersome tube, inventing the so-called air telescope and its better engineered eyepiece. In 1665, Cassini co-discovered Jupiter's Great Red Spot and used it to time the big planet's rotation. Huygens, applying Galileo's ideas, invented the pendulum clock and developed the balanced spring watch, both pivotal innovations in the study of space-time. Cassini published maps of surface markings on Mars, though Huygens had actually seen them first. And Huygens pegged the length of the Martian day at 24½ hours, just 7 minutes shy of the correct figure we use today. By getting parallax observations of Mars, Cassini was the first to estimate the size of our solar system. And Cassini used Galileo's method of measuring time by watching eclipses of Jupiter's moons to lay out lines of longitude on Earth. Endeavoring to perfect the geometry of optical lenses, Huygens developed the wave theory of light, setting the stage for today's quantum mechanics. Cassini explained the so-called zodiacal light, seen by astronomers as the reflection of sunlight off dust in the plane of the solar system. Toward the end of his life, Huygens determined liquid water to be a key factor in searching for extraterrestrial life, a quest now undertaken by the Cassini spacecraft and its Huygens probe. We've known Saturn as the ringed planet since 1655, when Christian Huygens explained what Galileo had seen 45 years earlier. But if you were standing on most of Saturn's moons, you'd have a hard time actually seeing the rings. Because most moons ride in the ring plane, you could only view them edge-on. From the right, watch tiny Prometheus, just 86 kilometers across, pass behind Big Tethys, 1,062 kilometers wide. Little Pandora scoots through from left to right. Here, medium-sized Mimas, traveling 14 kilometers per second, glides in front of the larger Rhea at 8 kilometers per second. When Cassini launched, 18 moons were known to orbit Saturn, and 13 more were suspected. By the end of Cassini's mission, astronomers will confirm 53, with another 9 marked as conditional. Only one of them is huge: Titan. In 1655, Christian Huygens was the first to observe Titan. Giovanni Domenico Cassini discerned Iapetus in 1671, Rhea in 1672, Dione in 1684, and Tethys in 1684. The sky-watching siblings William and Carolyn Herschel found Mimas and Enceladus in 1789. In 1848, Hyperion was spotted by the father-son team of William and George Bond in the US and William Lassell in the UK. Phoebe was the first moon to be discovered through photography by the American astronomer William Henry Pickering in 1898. Some of Saturn's moons are probably captured objects, particularly those in retrograde orbits like Phoebe. They orbit backwards in the opposite direction from the rotation of the planet. Each Saturnian moon is a unique jewel in the majestic planet's elaborate necklace. Before Cassini, no one suspected Enceladus to be anything other than a dead ball of rock and ice. But scientific sleuthing led to a remarkable discovery. Enceladus is about 482 kilometers in diameter. It would fit neatly between Los Angeles and San Francisco. The first good close-up, taken by Voyager 2 in 1981, showed the globe was remarkably bright and free of craters. In fact, Enceladus is the whitest body in the solar system. The first hints of a more complex story come from Cassini's magnetometer. The moon's magnetic signature looks more like that of a comet. Field lines are bent around Enceladus's south pole. A closer flyby shows the southern polar region has been recently resurfaced. Cassini's infrared spectrometer indicates the area is about 100 degrees warmer than the rest of the moon. And that heat signature aligns with 4 prominent tiger stripes appearing across the moon's southern terrain. They turn out to be fissures, cracks in the icy surface, each about 150 kilometers long and about 1 kilometer wide. Scientists name them Alexandria, Cairo, Baghdad, and Damascus. From each, jets of water vapor and water ice shoot out into space. Cassini eventually locates more than 100 of these geysers. Mission planners arrange more flybys and, in October of 2015, navigate within 50 kilometers of Enceladus's south pole and right through the jets, giving the instruments a chance to taste and smell them. It's mostly water ice. There's also some ammonia, methane, and carbon dioxide, key compounds associated with life. And hydrogen gas, which microbes, if there are any, could be using as a source of energy. Some of the particles are salty, like frozen sea spray, flavored by sodium and potassium. The science team imagines that a large subsurface ocean lies beneath the icy crust. As it sloshes around, carbon dioxide makes it fizzy, like bottled soda. When it finds a path to lower pressure through the cracks of the tiger stripes, it sprays out into space like champagne when the cork pops. Most of these salty water particles fall back to the ground as snow, decorating and repairing the surface of Enceladus. But some escape Enceladus's weak gravity. So Enceladus rides a misty ring of its own creation. Were the moon to shut off its water jets, this E-ring would dissipate completely within a few hundred years. Tracking and modeling icy tendrils made by interacting geyser jets lets researchers calculate how much mass Enceladus is pumping into Saturn's rings. Enceladus orbits in resonance with the moon Dione. Their dance is thought to heat their rocky cores. It's likely that Dione too has a subsurface ocean. Dione's big crater, Creusa, paints bright rays at least 500 kilometers across the moon's surface, giving researchers a marker of geologic time. Craters younger than Creusa disturb the rays. Older ones underlie them. Water is pulled down into the hot cores of these moons, re-emerging as steam through the seafloor. We know this because Cassini has detected tiny silicate particles that can only form in boiling water. In Earth's oceans, hydrothermal vents called black smokers and white smokers are oases for life. The churning hot water provides energy and sets nutrient particles swirling around. Is the same thing happening beneath the ice crystal crusts of Saturn's snow globe moons? To find out, future missions must look for amino acids, fatty acids, long carbon chain molecules, and perhaps microorganisms hitchhiking on the ice crystals, blasted far from the undersurface ocean depths. Many astrobiologists are fascinated by Titan because it is very cold, about minus 180 Celsius, yet it is wet. If anything lives on or inside Titan, it is almost surely not related to life on Earth. Titan is about the same diameter and mass as the planet Mercury, and Titan's surface gravity is about the same as Earth's moon. But unlike Mercury or the moon, Titan has a thick atmosphere, even thicker than Earth's, and scientists don't yet know why. It's the second largest moon in the solar system. At 5,150 kilometers in diameter, only Jupiter's Ganymede is wider. Titan is so much larger than the rest of Saturn's moons, it may have formed from the collision of several of its siblings. By mission's end, Cassini will have flown by Titan 127 times. Each pass gives the craft a gravitational acceleration equivalent to almost 1,000 kilos of extra fuel. When the two Voyagers sailed past in 1980 and 1981, they saw only this orange, smog-enshrouded globe. American and European scientists were so intrigued, they began sketching out what would become the Cassini-Huygens mission. 23 years later, an international team commands the release of the Huygens probe to land on Titan. January 14th, 2005. The European-built Huygens probe aerobrakes into Titan's atmosphere with its heat shield, deploys a parachute, and floats down for over 2.5 hours through a nitrogen-laden atmosphere. Its camera reveals an eerie landscape. Huygens lands softly in a slushy bank of frozen methane along the shoreline of a hydrocarbon lake. Huygens continues transmitting data for another half hour after landing, sending back images of rounded pebbles, probably made of hard, frozen water ice. Humanity has placed its imprint on yet another world. The flowing liquid on Titan is methane, which acts there as water does on Earth. In the range of Titan's temperatures, methane can exist in all three states: solid, liquid, and gas. It is not impossible that a form of life could be evolving on this moon, feeding on the constant rain of hydrocarbons, a true second Genesis, completely separate from our earthly tree of life. Since Voyager first glimpsed Titan, researchers have speculated that liquid oceans grace its surface. But dense orange smog has withheld the truth. This haze collects when the sun's ultraviolet light breaks up methane in the high atmosphere, forming long molecular chains that grow large enough to fall from the sky. These methane byproducts form snowdrifts into a huge network of dunes around Titan's equator. Cassini's camera was outfitted with near-infrared filters to peer through the orange fog to verify bodies of liquid. Images come back of relatively flat areas, but are they truly oceans? Or perhaps just methane slush? Or thick tar? The answer comes from Cassini's visible infrared mapping spectrometer. It catches a specular reflection, a bright spot of sunlight bouncing off a clearly liquid surface. With Cassini's radar, flat surfaces, lakes and seas, appear dark unless they are ruffled by waves. Titan indeed has oceans, ponds, and pools of liquid hydrocarbons, ethane, methane, and propane. Strangely, they form mostly in Titan's northern hemisphere near the pole. Saturn's eccentric orbit is to blame. Northern summer is warmer than southern summer on Saturn. But because of the way Titan is tipped, its southern summer is more severe, so all the southern liquid methane evaporates and rains out in the north. Over time, the whole system flips. In 15,000 years, Titan's lakes will all be in the southern hemisphere. This one, named Ligeia Mare, is larger than Lake Superior on Earth. It's probably 150 meters deep in spots. Mysterious frothy islands appear, bubbling up from under the surface. Titan holds a store of hydrocarbons about 10 times larger than all Earth's petroleum and natural gas reserves combined. Hovering 300 kilometers over Titan's south pole, a huge, persistent, toxic cloud of frozen hydrogen cyanide rotates ominously. This vortex seems to develop when Titan's southern hemisphere enters its autumn season. Titan thrusts its methane up into space at a frightening rate. The atmospheric supply can't last longer than about 20 million years. Something must be replenishing it. But what? Cassini's radar spots the answer. Mountains, some up to a kilometer tall. These may be cryovolcanoes. Some could be active today, spewing methane from within the moon. Cassini's radio science tools show Titan's whole body flexing in response to Saturn's gravity. That makes it warm enough inside to melt ice. Unlike the subsurface oceans of Enceladus with its rocky ocean floors, Titan's ocean is probably sandwiched between layers of water ice. So, if there's an underground marine layer, it may be sealed off from the hot chemistry of geothermal vents and any chance of nurturing life forms. Even after Cassini-Huygens, we still don't know how old Titan is, where it came from, or how long it's had an active atmosphere. Clues point to a cataclysmic event in the Saturn system, perhaps 100 million years ago, that either created Titan from smaller bodies or energized a barren, frozen Titan into an active system, possibly like the primitive Earth. To find out, we'll have to go back, float longer through the haze, sail the hydrocarbon seas, and soar through the nitrogen skies of Titan. To Galileo in 1610, the ringed planet appeared as 3 stars, with 2 small ones touching one large, prompting Galileo to declare that Saturn must have ears. But in 1655, using more advanced optics, Christian Huygens unmasked the apparition as a flat ring circling a spherical planet. 20 years later, Giovanni Domenico Cassini discerned that it was not one ring, but several, with gaps between them. The widest gap was later named the Cassini division. We now know that it's 4,800 kilometers wide and far from empty. In 1859, Scottish mathematician James Clerk Maxwell showed that the rings are not solid disks, but composed of many smaller granules. Each tiny fleck, pebble, and boulder revolves around the planet in its own orbit, jockeying for position among trillions of others. Though all are flying several kilometers per second, they jostle one another only very gently. The concentric rings are given letters, A through G, in their order of discovery. Material riding close into Saturn's cloud tops in the D-ring whips around Saturn in about 4 hours. But particles in the distant F-ring take at least 4 times longer. It wasn't until the Cassini's inspection that we learned just how flat the rings are. Incredibly, they are only 10 meters thick on average. From top to bottom, only about as tall as a 3-story building. These rings are 30 million times wider than they are high. And ring material can ripple up and down, crafting temporary corrugations. Many intricate wave patterns can be seen across the broad ring plane. Each one is conjured by a specific gravitational resonance with a Saturnian moon. Though the basic physics of the ring system is simple, it's mostly the product of gravity and collisions. The intricate structure of the rings is hard to mathematically model, even after 13 years of Cassini observations. The pressure of sunlight and forces from Saturn's magnetic field can push or pull smaller, less massive ring particles around. The mission team flies a series of special orbits that put the rings between Cassini and Earth. By beaming radio signals of 3 different wavelengths through the ring material, researchers build up a color map of particle sizes. Red areas hold more big particles. Blue regions contain mostly smaller grains. Radio waves, shown in the bottom half of this image, reveal finer structure than photos taken in visible light. Most particles are small, from tiny crystals smaller than a dust grain, up to pebble-sized. Less common are ice rocks and large boulders, up to the size of houses. A few are the size of mountains, moons in the act of forming or falling apart. Grabbing an average-size ring particle would feel something like closing your hand around a thick layer of very cold whipped cream to find a glob of solid ice cream deep inside. The packing of particles varies between rings. Very little light gets through the B ring of crowded snowballs. An astronaut would have to dig her way through it. The A ring is less congested, and the G ring is very diffuse, like fog or smoke. The Cassini mission confirms the rings are made of almost pure water ice. But tiny quantities of simple organic compounds tint and shade them. The astronomer Carl Sagan called these colorful chemicals tholins, Greek for muddy. Crossing Saturn's dark side, Cassini's camera picks up the true colors and intricate complexity of the ring plane's variations. Subtle gravitational effects fashioned by the many moons sculpt the ring material. Small moons, this one's named Pan, orbit within the rings. They seem to sweep clear their lanes of travel. The moon Mimas, gravitationally combing the ring's particles, causes the large Cassini division. Other rings are herded into form by so-called shepherd moons, like Prometheus and Pandora. Tiny Daphnis, just 8 kilometers across, pushes a wave of ring material like the bow wave of a boat on a lake. Daphnis bobs up and down like a merry-go-round horse, gravitationally pulling particles into dune-like mounds 3 kilometers tall. It has plowed a 35-kilometer-wide furrow in the ring field called the Keeler Division. The larger Pan forges the 325-kilometer Encke gap in Saturn's A-ring, giving it a wavy edge, and Pan's gravity inspires a spiral wake of particles. Based on that gap, researchers predicted Pan's existence in the late 19th century, long before it was first seen. But no one anticipated Pan's remarkable shape. And it's not unique. The slightly wider moon Atlas has a similar structure. Both wear skirts of gravitationally attracted icy crystals. Certain small satellites on eccentric orbits repeatedly crash through the F-ring, leaving behind sets of disruptive splashes as evidence of their passing. Other minuscule moonlets, too small to be seen, fashion propeller-shaped resonant waves in the snowy rings falling around Saturn. The ever-evolving complexity of these ring circles moves like a musical score, playing in silence. Once every 14 years, the ring plane lies exactly edge-on to the Sun. Cassini was present for one such equinox. In essence, the sunlight on the rings has been switched off, and they cast no shadows on Saturn. They are only visible because Saturn reflects some light on them, here digitally multiplied many times. Only the F-ring, which is slightly tilted from the others, catches any sunlight. But because the rings are so thin, any tall structure within them throws its shadow onto the ring plane. Thus, in the outermost edge of the B-ring, a surprise appears. Hundreds of long shadows mark a field of icy spikes. Geometry dictates these points must range up to 1 kilometer or so in height. Like icebergs growing in a sea of mostly empty space, these thorn-like clumps may be molded by the invisible fingers of a gravitational resonance with one of the moons. Or they may be drawn out by static electricity inspired by Saturn's magnetic field. Some of Saturn's rings are constantly morphing, while others are stoically consistent year after year. How old are these bright, icy rings? They may have formed in the last 100 million years, when icy moons or comets collided or were torn apart by Saturn's gravity. Or they might be as old as Saturn, the leftover debris of the solar system's birth. Cassini may yet find the true answer. Looking down at Saturn's North Pole, Cassini gets a spectacular view of the globe's jet stream. Some resonance of the wind energies banks the stream into a six-sided shape, a hexagon. Apparently, an eastward-flowing shallow jet stream is bumped by occasional storms. The jet reacts by settling into the most stable geometric shape: 6 roughly equal sides. This polar monsoon is about 32,000 kilometers wide. You could fit 2.5 Earths into it. Its winds blow faster the closer they get to the pole. Up to 540 kilometers per hour. Why kill Cassini in a ball of atmospheric fire? The international scientific community has agreed to avoid any possibility of contaminating Saturn's moons, especially Enceladus and Titan. Cassini is warm inside, essentially room temperature. Any microbes that found their way in during assembly could have easily survived. And Cassini's RTG will remain hot for decades. If she was allowed to accidentally crash on Enceladus, Cassini might easily melt her way down through the ice into the underground ocean. Back in 2009, studies had showed Cassini had enough fuel to go beyond Saturn to explore the ice giants Uranus or Neptune. She could have been sent back to Jupiter or outward to visit a population of comet-like asteroids known as the Centaurs. But to get all the science possible from the Saturn system, Cassini would have to die here. That led trajectory designers at JPL to develop a jewel of orbital dynamics, the Solstice mission. The plan optimizes repeated flybys of Titan. The route features high orbits to look at the poles and the rings, long loops to map the planet's magnetic fields, flattened equatorial orbits to check out moons, and ending at the peak of northern summer to mirror Cassini's arrival in southern summer. Between the two, scientists can infer the full cycle of Saturn's seasons. The science based on Cassini's data will go on for decades. Nudging Cassini's speed by just 8 meters per second is enough to begin her death spiral. The craft makes repeated dives between the innermost ring material and the roiling atmosphere. These maneuvers would have been far too dangerous to contemplate when Cassini was designed. Along the way, the spacecraft maps fluctuations in Saturn's gravity and magnetic fields and samples icy particles flowing in from its rings. Until the very end, Cassini beams science data and images directly to Earth. Finally, on September 15, 2017, as the Cassini spacecraft streaks along Saturn's clouds, its high-gain antenna shifts away from Earth. The signal fades, and she is gone.